This presentation is designed to cover the architecture of the acquisition systems for electrophysiology. Materials are prepared within the Erasmus Strategic Partnership Project under the title Innovative Teaching Approaches in Development of Software Designed Instrumentation and its Application in Real-Time Systems. Lectures include theoretical background, but also include explanations and demonstrations of practical examples in the field of electrophysiology measurements. Lecturers, Assistant Professor Milica Jankovic and Teaching Assistant Marija Novicic, are employed at the University of Belgrade School of Electrical Engineering, Department of Signals and Systems. Also, they belong to the Laboratory for Biomedical Instrumentation and Technology. Many organs in the human body, such as the heart, brain, muscles, manifest their function through electrical activity. This type of electrical potentials, that we call biopotentials, are generated by cells. The cell is basic, structural, functional, and biological unit of the organism. When the cell is active, her potential is called action potential. Electrophysiological signals represent the sum of the potentials of individual cells. Heart cells produce a signal called the electrocardiogram or ECG. Brain cells produce a signal called an electroencephalogram or EEG. Activity of muscles such as contraction and relaxation produce an electromyogram or EMG. ECG, EEG, and EMG are the most currently used electrophysiological signals. There are also some other types of electrophysiological signals, such as eye movement potentials, retinal potentials, stomach activity, lung activity, but in this lecture, the focus will be on ECG, EEG, and EMG signals. 70% of the human body is made up of water. The human body contains many salts that dissociate in the water into ions. Biopotentials are ionic potentials produced by ionic currents in the organism and have to be converted into electrical potentials before being measured by conventional methods. Electrodes are sensors that can do this type of conversion. What is the role of data acquisition system for electrophysiology signals? It should allow the acquisition, processing, and visual presentation of biopotentials that are of interest for diagnosis and therapy. Also, it should enable easy exchange of data between different workstations, and finally, application of intelligent modules for automatic diagnostics. The first module of the data acquisition system for electrophysiology monitoring is analog front-end that includes circuits for analog signal processing like amplifiers or filters. The second module is analog to digital converter. Discretized data could be transferred wirelessly to the computer or to some cloud. The last module includes data visualization, additional digital signal processing and data logging. And in this lecture, 5 practical examples will be presented, and the designing of the appropriate software will be demonstrated in detail. Different software environments could be used for designing data acquisition, visualization, and data logging. In this table are compared options for general-purpose software environments like C, C++, C#, Java, and application-specific software environments like LabVIEW, DAISY Lab, and MATLAB. The pre-acknowledged level, community size, the complexity of application possibilities, and the built-in libraries for data acquisition and analysis are different. For beginners, DAISY Lab environment is the easiest way to learn data acquisition programming, while general-purpose software requires high-level programming skills. However, the community size is much larger for using of general-purpose software. Extremely complex applications could be developed using LabVIEW and general-purpose software. Data acquisition drivers for a wide range of devices are available for LabVIEW and DAISY Lab. Finally, application-specific software environments have a rich repository of data analysis libraries with a lot of ready-to-use examples. Before choosing the appropriate software environment, there is a series of questions that you need to answer. The first issue is considering financial aspects. Can you afford a commercial software environment, or you have to use open source environment? Within this issue, there are several questions that you need to answer. Is the price of the software the key for selecting the software? Do you need the constant support, or do you need the guarantee for the functionality? What is the price for distribution of developed applications to users? Another aspect that you need to consider before the selection of the software environment are: how much time is planned to develop the application? Do you need the software environment that is extremely stable and reliable? Is it possible to use the software environment in your operating system? How much time is planned to maintain the developed application, and how much time you need to upgrade your application to the newer version of software environment and to the newer version of operating system? There are too many questions that you need to answer before choosing the appropriate software for your application. Demonstrations within this lecture will be based on using LabVIEW software environment. The acronym LabVIEW means Laboratory Virtual Instrument Engineering Workbench. It is a system design platform and development environment for a visual programming language. It is designed to make the data acquisition programming easier to engineers. Examples in this tutorial will use 2 additional LabVIEW toolkits: Biomedical Toolkit and Advanced Signal Processing Toolkit. Installed data acquisition driver is DACMX. Practical examples are based on using USB 6008 multifunction data acquisition device. 5 practical examples in the field of acquisition of electrophysiological signals will be presented within this lecture. The first example will explain how to make a basic data acquisition. The second example includes the demonstration of acquisition system for testing impedance of electrodes. Next demo explains the setup for electrocardiography recording and includes the solution for real-time heart rate monitoring. The fourth example shows electroencephalography acquisition and an application of steady-state potentials. The last example demonstrates the design of application for fatigue detection based on continual muscle activity monitoring using surface electromyography.